Hey everybody, this video is not really introducing any new concepts. There were enough in the last video, right? Work and the work energy theorem, things like that. We're going to see how work often appears, how it often shows itself in the form of a graph. And then after that, we'll look at an example problem. Now you should definitely, especially if you're in my own physics class, definitely pay attention, and I'd recommend you take notes when we do this first part. The second part, though, is just a sample problem based on stuff we learned from the last video. So if you feel like the last video went well, if you felt like you could do everything, maybe this part is a bit more optional. Okay? Let's go ahead and jump into the part that is very important, because this is a very common thing that shows up on the AP Physics 1 exam. And that is something known as a force versus displacement graph. And what it is, well, exactly what it sounds like. I have here a graph. We're used to, in this class, seeing graphs with time on the x-axis. That's been, I think, all of our graphs up until this point. But you could have a graph, certainly with displacement. Ultimately, of course, you could put any kind of thing you want on a graph. Here, this is a graph of force on the y-axis and displacement on the x-axis. So what does this mean? Imagine maybe I'm pushing a table, I'm applying a certain amount of force, and that force might change as the table is moving. Not through time now, but moving across, say, the table. Okay, so, if the table started here and then it was moving, right? The distance, or the displacement technically, is going to the right. Well, maybe I'm applying a different force. Like, maybe I'm applying this force of 5 newtons for a while, but then when I get close to where I want to ultimately push that table, when I get close to the end spot, well, I drastically lower my force to 0. So it's how much force I'm applying on an object versus the displacement, the change in position of that object, okay? It could be for a single pushing force. If I call this force P, maybe this is the pushing force P. You might also see a graph where it's the net force. So let's see, maybe just for fun, even if you're not sure why right now, you're just going to trust me. Let's find the area under the curve for this red section. What's the area under the curve? We've kind of done something similar. We've thought about looking at these certain values for other graphs. Area under curve. When I say under the curve, I mean between the x-axis and the line. For the red section, I'll call that area 1. What's in red? So for area 1, it's simply a square. The area of a square is base multiplied by height. The base is, let's see, I go from 0 to 5, so the base is 5. And what's the height? Well, it's from 0 to, 5, easy. Now, to be fair, this is a physics graph. It's not just the two numbers 5. The base is 5 meters, and the height is 5 newtons. So when I multiply that, that's 25 meter newtons, or I could just as easily write Newton meters. That's the same as 25 joules. Oh, I bet you already know the punchline. The area under this curve is the work that is done. Oh, the area, this is our big idea. Area under a force versus displacement graph gives us the work. Oh, very interesting. This graph I have seen on every single AP Physics 1 College Board exam as of this video, 2021, the fall. It is a very common graph to give you. So you might see this graph and like, okay, I got it, force and displacement. Maybe they're asking about the work. If you don't recognize that the area under the curve gives you the work, you might be stuck. Now, what if I asked to find the area of the curve for E.2? Could I do that? Yeah, I mean, that's pretty easy, right? It's a triangle here, this E.2. So the area under a triangle is 1/2 base times height. So that's just going to be 1/2. Well, I still have a base of 5 meters, and a height of, now the height here, well, it starts out at that same spot, 5 newtons. Well, that's going to be half of 25. That's 12.5. 12.5 joules, 12.5 newton meters. So the total, and you could do that, it kind of depends on the problem. The total would be 25 plus 12.5. Or maybe you were just finding the work, the area under the curve, for a certain section. So the area under the curve gives you the work. Okay? That is a very important thing to know. But I can go one step further. Let's say, in fact, this was looking at the net force. Sorry, I can't exactly write horizontally or vertically. Let's say this was the net force. So, maybe I had some pushing force here. There was some frictional force. The sum of the forces in the x direction, maybe it's P minus F equals ma. let's say what this diagram is it's the net force, okay? It would have to maybe say that in the problem, but let's say it is. Let's say it's the net force versus displacement. Well, the area under the curve would be the net work. Oh, okay, right? It's the same thing, just like the area under the curve for the last slide would have been the work for that force. The area under a graph with the net force versus displacement would be the net work. And by the work energy theorem, the net work is equal to the, do you remember? The change in kinetic energy. Often written as delta K. Sometimes I'll write it as delta KE. That's also pretty common. So what does that mean? If I could find the area under the curve, that's equal to 1/2 mv squared minus 1/2 mv naught squared. This is also very common on the AP exam. They might give you this graph. Maybe they say like, oh, the object starts at a velocity of 0. It starts at rest. Calculate the final velocity from this graph. And in fact, while it might seem like a really tough problem, you can do that. Because if this is the net force, you could find the area. That's what you would plug in right here. And then you could solve for the velocity by the work energy theorem. So really what's important, it's kind of two levels. What's kind of important, do you recognize that the area under the curve is work? Okay, if you remember that, pretty good. But even better, the area under the curve, if this is a net force graph, that's the change in kinetic energy. I'm going to write it like this, the change in kinetic energy. So you could easily go from this graph to finding, say, the change in velocity of an object. That is again, very common problem on the AP Physics 1 exam. I often see it multiple times on the same test, maybe multiple choice questions, or maybe sometimes I see it on multiple choice, sometimes on free response, but this graph shows up a lot. And if you can remember this, it should be an easy problem if you can remember this detail, okay? So for a force versus displacement graph, the area under the curve is the work, or it's the change in kinetic energy if it's that net force versus displacement. That's the new physics for this video. That was 7.5 minutes, not too bad. The next part of this video, part B, this is the part that's kind of optional. I have here a sample work and work energy theorem problem. This isn't even really using the graphs I just talked about. So if you did, especially if you're in my class, if you watched the last video and you thought it went okay, if the last homework seemed to go okay, maybe you don't have to watch this. But this is good practice, and it's good to see me work through a problem if you're struggling. So here's my recommendation. You could just stop watching, or maybe you hit pause and you try this sample problem. And then after you try it, watch the video as I solve it, okay? So here's the problem. I'm pushing the box, or some person is pushing a box. It gives some details right here. There's a part A and B. Try it. Try hitting pause and try the problem, and then hit play. Okay, did you try it? Part A says, after being told that we have a 15 kilogram box, so this right here is 15 kilograms, it starts at rest, so the initial velocity is 0. Okay, we're applying this pushing force. There's some pushing force P, and there's some frictional force we'll call F. It's asking in part A to calculate the net work on the box after moving a distance of 7 meters. Okay, so it's asking for part A, what is the net work? Well, if you remember the last video, that's going to be the net force, and you could write it like this, or, if you wanted to write it like this, that's okay. Either one would be acceptable. Okay, I'll stick with my first one for right now. What is the net work? It's the net force multiplied by the displacement. Now, maybe technically, especially if you're really trying to show all your work in the x direction, you could say, okay, right is positive. I have a pushing force. I have a frictional force. That equals ma. Now, normally, we would say right is positive, so the frictional force would be negative. I'd be subtracting that. Now, I don't know the acceleration. Maybe you could calculate it, but this right here, this is the net force. And it turns out that I gave you these numbers. The pushing force was 85 minus the frictional force of 78. What's 85 minus 78? Well, 85 minus 78 is 7. I hit pause and I moved up some of this so I had a little more room if you notice those kind of swap positions. 85 minus 78, that's simply 7. that is the net force. P minus F, that's the net force, so that's 7. So what's the net work? It's 7 newtons multiplied by 7 meters. 7 times 7, that's 49. Okay, that's a newton meter or a joule. So 49 joules. Should this be positive or negative? It should be positive because the net force is in the same direction as the displacement. 85 newtons, the pushing force was more than the 78 newtons of friction. Okay, so the box is moving to the right, the displacement is to the right. I should have a positive amount of work. That's part A. Nice, did you get it? Let's look at part B. So I knew that the net work was equal to, I'll just write it right here, it's equal to 49 joules. For part B, it's asking about the final velocity. Oh man, now the final velocity. Now, if you approach this problem by thinking, well, okay, if I do that sum of the forces, I could maybe solve for the acceleration. And then if I had the acceleration, maybe I could use one of my constant acceleration equations. You could totally solve it that way. But here's the nice thing about energy and the work-energy theorem. It is often easier than the equations we've been doing in our last set of videos. While this is totally accurate, your physics here would be totally acceptable, we can use the work-energy theorem to just use a single equation. What do I mean by that? Well, remember the work-energy theorem. It says the net work is equal to the change in kinetic energy. The change in kinetic energy is 1/2 mv squared minus 1/2 mv naught squared. Don't forget, it's always the final minus the initial. Students will often flip those. They'll accidentally flip them and you'll get the wrong answer. You'll get a negative when it should be positive. So if I know the net work, I can set that equal to 1/2 mv squared minus 1/2 mv naught squared. Let me get my cursor again, 1/2 mv naught squared. The initial velocity is 0. So 1/2 mv naught squared, this whole thing goes away. The net work was 49. So 49 equals 1/2 mv squared. And then let's see, 49 is equal to 1/2. The mass is 15. I don't know what v squared is. So 1/2 times 15, okay, and then divide that out and then take the square root. I check my calculator and let me know in the comments if I made an error. But when I solve for this, I get 2.56, approximately. Maybe you rounded slightly different, meters per second. That's the final velocity. And notice, I could do that whole thing with just a single equation. This work-energy theorem is very valuable because it directly relates work, and of course that means force and displacement, directly relates work to velocity. It would have been easier, at least in my opinion, than doing two separate equations. So the work-energy theorem is valuable. That's how you could solve and get the final velocity. Okay? That's it. That's my sample problem. If that went well for you, great. If not, maybe re-watch that first video or maybe carefully watch these solutions again. But that's all for me. I'm hanging out. See you later. I'm heading out. Bye.